Okay guys, so basically keeping in mind the limitations of the valence bond theory, that is, it was not able to say that which ligands were strong, which ligands were weak, and also it was not able to say, or it was not able to judge what would be the color of the complex. So there was many much such limitations with respect to the VBD. So keeping in mind the limitations of the VBD, a new theory was proposed in order to overcome all the limitations of your VBD, and that theory was called as crystal field theory, which is also known as CFT. So as per this theory, it is having some prior assumptions. First and the foremost thing, it considers the metal ligand bond as an ionic bond. That is, there is an existing an electrostatic force of attraction between the central metal atom or the ion and the ligand. The second, it assumes the anionic ligands as the point charge, as a point charge. And the third most important thing is, it is considering the neutral ligands as that of your dipoles, having both the polarity, that is positive as well as the negative. And according to this theory, it is mainly assuming the concept of your, or it is mainly taking in the concept of d orbitals. D orbitals. And with respect to this theory, it says that whatever the 5 sets of orbitals of d are present, 5 set of d orbitals, so they are having the same energy in the absence of ligands. In the absence of ligands. So this is called as what? As a degenerate. Degenerate. That is, the orbitals which are having the same energy, that orbitals are called as that of your degenerate orbitals. And it further explains that whenever these d orbitals of the central metal atom or the ion, in the presence of the ligands, that degeneracy is lifted. Or in simple words, we can say that the 5 d orbitals get split off in the presence of your ligands. And this CFT has mainly concentrated a splitting of the orbitals with respect to that of your octahedral complexes and tetrahedral complexes. That is, the central metal atom or the ion is bounded by 6 ligands, they are called as an octahedral, whereas the central metal atom or the ion is surrounded by 4 ligands, it is called as that of your tetrahedral. Now we are going to see the crystal field theory with respect to octahedral complexes. So according to this, it says that whenever a ligand is approaching your central metal atom or the ion, your orbitals are getting split up into 2 sets. That is, one set will be of higher energy and another set of orbitals will be of lower energy. And in a mere explanation, it says that the orbitals, that is the d orbitals which are in between the plane, that is, we know that the d orbitals as dxy, dyz and dxz. Similarly, this means what? These 3 sets of orbitals are in between the plane, whereas dx square minus y square and dz square, they are on the plane. For example, if I say this one as your x and y axis, the dx square minus y square orbital will be in this way, that is, they are in the plane. Similarly, dz square, if I consider this one as a z axis, we know that it will be in the plane. But when I consider these 3 orbitals, I am just writing, they are in between the plane. If you choose this one as x and this one as y, they are in between the plane. If this one as y and this one as z, they will be in between the plane. So it says that with respect to the octahedral complexes, the electrons which are present in dxy or dyz and dxz, they will have a less repulsion from the electrons of incoming ligands. Similarly, the electrons which is present in dx square minus y square and dz square, they are having the more repulsion from the electron of incoming ligands. And that is the reason what happens, these three sets of orbitals in that of your octahedral will be having a lower energy, whereas these two sets of orbitals which are on the plane will be having the higher energy. So when we see this splitting pattern, you will be getting a clear-cut idea. That is, in the absence of the ligands, let me write it as the 5 sets of orbitals is in this way. They are in the absence of ligands, the d orbitals will be degenerate. That is, they are having the same energy. As the ligands are approaching this center d orbitals, they will be somewhat higher in energy. But also their degeneracy is not lifted till now. But when the ligands are completely surrounding your central metal atom or the ion, it gets split up into 2 sets with respect to that of your crystal field theory. So with respect to your octahedral particularly, the 2 sets will be how? That is, the down set will be 3 orbitals. They are your dxy, dyz and dxz, and the upper part of higher energy will be your dx square minus y square and dz square. So in octahedral part, these 3 sets of orbitals is called as a T2g, and this 2 set is called as it of your Eg. So whatever the magnitude of this splitting is there, that is represented by your delta naught, which is called as crystal field splitting, which is nothing. We can easily define the crystal field splitting as the splitting of the 5 degenerate orbitals into 2 sets of orbitals in the presence of ligands is called as crystal field splitting. So whatever the splitting we are observing, it is mainly in the presence of ligands. Yes. So now, as we all know that VBT was not able to explain which ligand is weak and which ligand is strong. So before going to that one, I will just make sure that the part in between, if you draw just a straight line, this is called as that of your Barry center. So when you are observing the Eg set of your octahedral, it has been raised in the energy of 3 by 5 times of your delta naught, whereas your T2g set has been decreased by a value of 2 by 5 times of your delta naught. Very much important. Okay, so now depending upon the magnitude of your delta naught, crystal field come across a concept of distinguishing your strong and the weak ligand. So according to the crystal field theory, he says that ligands which causes a large crystal field splitting or which provides a higher magnitude of this delta naught, they are called as a strong ligands. That is, the ligands which produces or which leads to a large crystal field splitting. So that is called as what? As a strong ligands. Similarly, he also explained with respect to weak ligands as ligands which causes a small crystal field splitting. So they are called as what? As a weak ligands. By the experimental demonstration, he has also arranged a series of ligands with respect to their magnitude of the crystal field splitting, and that series is called as spectrochemical series. According to which the series lies in this way. First is your iodide, which is smaller than that of your bromide. which is smaller than that of your thiocyanate, which is smaller than that of your chloride, which is smaller than that of your sulfide, fluoride, hydroxide, oxalate ion, water, thiocyanate, EDTA 4 minus, then is your ammonia, then is your ethylene diamide, then is your cyanide, and then at last is your carbon monoxide. So arrangement of the different ligands in the increasing order of their field strength is called as that of your spectrochemical series. So in this spectrochemical series, the ligands which are at the lower end, that is in this part, which is your left hand side part, they are called as that of your weak ligands, and which are at the higher end, they are called as that of your strong ligands. That was the reason when we were dealing with the VBT, whenever ammonia came, we call it as a strong ligand. You could just see that it is lying over here. But when it came with respect to your chloride or that of your fluoride, it was called as a weak ligand. So this gives us the particular knowledge that which ligand can act as a strong ligand and which ligand can act as a weak ligand. Remember, your CO is one of the strongest ligand and iodide is one of the weakest ligand. So using this concept, we limited whatever the first limitation of VBT was there, that was majorly clarified with respect to that of your crystal field theory. Now the question arises that how the electronic configuration will be present with respect to this crystal field theory. That is, we came to know that in an octahedral complexes, if I consider, the splitting was in this way. That is, the first set is called as that of your EG set, the second set is called as that of your T2G set. So EG set was higher in energy, whereas T2G set was in the lower in energy. But what you can say with respect to the configuration, for example, if you are having a D1 electron, where does it accommodate? Of course, if you write the box diagram, it will be more clear for you. Yeah. So first, it is split up into 2 sets, and second one, it is having a 3 set in this way. So of course, when a D1 is present, we know that it will be accommodating a lower energy, that is over here. When it is having a D2 configuration, of course, according to following the Hund's rule, it will be accommodated over here. In case of your D3, it will be accommodated over here. Yes, but now the question arises, where does this D4th electron goes? In case if your central metal atom or the ion is having a D4 configuration. Now the question arises whether it will be pairing in the T2G or whether it will be jumping to that of your EG. In order to clarify this, here we have to come across a concept called as that of your pairing energy. Pairing energy, which is denoted by a letter of P, which states that the energy required for the pairing of electrons. So according to this concept, it states that there are mainly 2 cases. Case 1, that is, it says if delta naught is greater than P. Of course, what happens, whatever the difference is over here, that is called as what as delta naught. So in case if delta naught is greater than P, that means what? It has been having a higher crystal field splitting. So what happens? The electrons will not able to jump to the higher energy. In turn, what happens? Electrons get paired up, giving you the configuration as what? T2G4 and an EG0. So this is mainly observed in case of that of your strong ligands. When you consider with respect to the case 2, it is with respect to delta naught is less than P. So in this case, what happens? The crystal field splitting is very much small. So the fourth electron can easily jump to the higher energy orbital, giving you the configuration as T2G3 EG1. So this is mainly observed with respect to that of your weak ligands. So by this way we can easily say that if an central metal atom or the ion is having a D4 or D5 configuration, how does the configuration lies with respect to the magnitude of your crystal field splitting. So now, as usual, if I consider with respect to the tetrahedral complexes, of course now whatever we have did was with respect to the octahedral. Coming in tetrahedral, you have to just keep in your mind, it is just the vice versa concept of your octahedral, that is the opposite concept of your octahedral. So here the splitting will be followed in such as the same way. The splitting is into two sets, but remember here the T2G set will be of higher energy, that is dxy, dyz and dx square minus y square will be of higher energy, whereas the EG set will be of that of your lower energy, that is dx square minus y square and that of your dz square. So whatever the splitting magnitude is there, that is represented by as delta T. Of course, from the barycenter, your T2G set has been increased by an energy of 2 by 5 times of your delta T, whereas your EG set has been decreased by a value of 3 by 5 times of your delta T. If we will consider the comparison between the both crystal field splitting, you can easily say that your delta T is 4 by 9 times of your delta naught. 4 by 9 times of your delta naught. Very much important with respect to solving your competitive exam solutions or problems. Mainly they will be depending on these equations. That is delta, that is crystal field splitting with respect to tetrahedral complex is 4 by 9 times of your crystal field splitting in octahedral complexes. Now let us solve some problems. For example, we have given you as K2 CO C2O4 thrice. This is a complex and they have asked for give the oxidation state, give the coordination number and d orbital occupation in the complexes with respect to VBT. So first let us find its oxidation state. So of course K is in the +1 state. So each K means +1, so it is having +2. Cobalt I have to calculate, let me take it as X. C2O4 is a bidentate ligand, so it's also an anionic ligand, so plus of 3 times of your -2. Overall complex is not having any charge, so it is equals to 0. So X is equals to what happens? 6 minus 2, 6, yeah. So this is your K3, not K2, sorry. It's your K3 in the given example. So 6 minus 3, that is equals to 3. So the oxidation state of your cobalt is +3. Coming with respect to its coordination number, we know that it is the number of the donor atoms of the ligands which is binding your central metal atom or the ion. It is not just the number of the donor atoms of the ligands. What it is saying, coordination number, it is the number of the donor atoms of the ligands which is binding your central metal atom or the ion. Since it is a bidentate ligand having 2 donor atoms and both the donor atoms are binding your ligands and there are 3 such bidentate ligands, so coordination number is 6. No problem with that. But when it comes with respect to the d orbital configuration, we know that oxalate is a strong ligand. So oxalate being a strong ligand, what happens? For example, if I write as cobalt. So cobalt ka general atomic number is how much? 27. But in the complex it is having a CO +3. That is, if I write for 27, I will be getting as argon 18, 19, 20, 3d7. So CO is in the +3 state. So I will be having the configuration as argon 3d6. So So with respect to the crystal field splitting, it is an octahedral complex. 3 2s are 6. So there are totally a coordination number is 6. So it's an octahedral complex. So I know that the splitting yes. So this is in the two sets. One will be of E2 set, EG set, and another will be your T2G set. Is that true? Okay. So what happens? We know that 3 electrons first it will accommodate over here. But the other 3 electrons, whether it is going to jump or whether it is going to pair up. Since we know from the spectrochemical series, our oxalate is a strong ligand. So what happens here? Delta naught will be very much greater than the P. So what happens? Here pairing takes place. So resulting in a configuration of T2G6 and an EG0. Is that clear? Coming to the next part is they have given as NH4 twice and that of your COF4. Remember, it is not as an NH3, they have given as NH4, ammonium. So it's a cation over here. And the complex is here complex anion. So here we'll be having as plus 2 plus x of minus 4 is equals to 0. X is equals to plus 2 state. So cobalt is in the plus 2 state. Remember, it's a tetrahedral complex. Why is it a tetrahedral complex? The coordination number is how much? 4 fluorine atoms are present. So coordination number is 4. It's a tetrahedral complex. So we know that CO is having a configuration as argon 4s3, 4s2, 18, 19, 20, 3d7. But cobalt in the plus 2 state will be having as argon 3d7. And from the crystal field splitting, we know that in tetrahedral also we are having the 2 splits. But how is that? Higher part is your T2G and lower part is your EG. Yes. So what happens? The 7 electrons will be accommodated how? Given is your fluorine, which is a weak ligand. So the concept lies over here. Delta naught is less than that of your pairing. So easily the first electron will come over here, second electron will come over here. The next 3 electrons, third, fourth, fifth, yes, and then sixth and seventh. One, two, three, four, 5, 6, 7. Giving you the configuration as EG2 T2G5. Is that clear? The next concept you have to come across, which is called as that of your color of the complex.